Hi, class. So this is the last lecture for chapter 13. I'll be going over chapter 13.4. It's solving equilibrium problems. And we'll be working on worksheet 13. You'll probably need to have your calculator, a scratch pad available. The PowerPoint that I'm going to show is fairly short. And then these problems are fairly lengthy, so I've already solved them on the worksheet. I'm just going to go through them step by step. And you can write these down, or you can simply maybe take a screenshot or something, stop the video, take a picture of it, and then use that. Okay, so let's go to my screen share. Okay, always do. Let's see. All right, so chapter 13.4, equilibrium calculation. So the learning objectives for this chapter section is to learn to use equilibrium constant expression to solve for equilibrium concentrations in systems that are at equilibrium. So in this case, you will have, in the equilibrium expression, you'll have enough information for the components in the reaction at equilibrium to be able to solve for one unknown. So all of these problems require some algebra. The second one, for systems not at equilibrium, is the most common problem. And a little bit more involved. So this is an introduction to solving these problems. As we go on to chapters 14 and 15, there are other variations on solving these equilibrium problems that we will learn. So let's see, let's look at calculating concentration from equilibrium concentration. So here's a reaction. This is a pretty familiar one by now, N2O4 going into 2NO2 with a equilibrium constant equal to 0.00464. So it says at equilibrium, calculate the concentration of NO2 for this reaction if the equilibrium concentration of N2O4 is 0.400. So you need to start with a balanced equation. I'm not sure if that's what I have here, but you have to make sure the equation is balanced because the stoichiometry is very important in these problems. So in this case, if we look at the equation, N2O4 going to 2NO2 is a balanced equation. So that's fine. We can check that box off. So we'll write the equilibrium expression as we learned previously. So Kc is equal to NO2 squared. It's product squared because of the coefficient 2. So we put the square up there, divided by N2O4. Now what we know is that N2O4 is 0.400 molar. So what we can do is we can just plug that in. Well, I guess what I did first was rearrange it to solve for NO2. So if we rearrange to solve for NO2, we need to do a little algebra. We get NO2 is going to equal to Kc times N2O4. And then because NO2 is squared, we'll take the square root of that. We plug in the values and solve it. And we're going to get 0.0136. So many of these solutions require you to take the square root. Well, when you take the square root, you get two answers, right? You get a plus and a minus. So actually the answer for this problem is a plus minus 0.0136. What you have to choose is which of those answers is correct. Well, negative 0.0136 is not. not possible. And that doesn't make any sense because the concentration can't be negative. So the only correct answer is 0.0136. So that's not too hard. So if you know the equilibrium concentrations in the problem, if the problem gives you the equilibrium concentration, it's not very hard to calculate the other ones. A few algebra manipulations, and you can set up an equation that will allow you to solve for the unknown. So here's a summary of what we need to know. I mentioned this before. Is the equation balanced? They're all given concentrations in molarity. If not, do the appropriate calculation to determine molarity. So remember, equilibrium expressions require the concentration to be a molarity, or if it's a gas reaction, pressure. Thirdly, set up an ice table. So this is a problem, this ice table. The ice stands for initial concentrations. C stands for change. That's the quantity that changes to reach equilibrium. And E equals the quantity at equilibrium. And those are the quantities that you'll use in your equilibrium expression. So this is what you would use if you don't know a lot about the equation. You only have a few of the concentrations of the substances that are in the equilibrium expression, and they're going to change. So use an ice table. You may have heard of that before. So here's another reaction. Let's look at this one. We're going to use an ice table to solve this one. We have H2O plus CO is in equilibrium with CO2 plus H2. The equilibrium constant is 23.2. So one thing to notice when you look at this equilibrium constant is that it's greater than 1. We talked about that before. So this equilibrium will favor the product side. There'll be more products than reactants. So it says if the initial amounts of H2O and CO, those are the reactants, are both 0.1 molar and 0 molar CO2 and H2. So H2O and CO are both 0.1 molar, but the products are 0 molar, there's nothing. What will the equilibrium concentration be of both products? Actually, what will the equilibrium concentration be of everything, of H2O, the CO, the CO2, and the H2? So not only the products, but everything else, because if you don't have any product to begin with in this problem, it means that Q is 0. So if Q 0, it means we've got to make some product. And if we make product, we're going to lose reactant. So the equilibrium concentrations of everything are going to change from what they are initially. All right, so let's set up our ice table. So this is what an ice table looks like. We have our reaction, the reactants above the table. So I have H2O in one column, CO in another column, CO2 in a third column. That's the product in H2 in the last column. So usually that's how I set it up, is the reactants first and the products last. We have 3 rows, the initial concentration written in the first row, the change that's going to occur in the second row, and then what that's going to look like at equilibrium in the last row. Now the change is where we include a variable. So we don't know what that's going to be. That's what we have to solve for, is that change. And so in this case, what we know is that H2O is 0.1 molar, CO is 0.1 molar, CO2 and H2 are 0. So the change is going to occur. We're going to give that a value X. So we say that CO2 and H2 are going to be formed in X amount at equilibrium. And when that happens, it means that we're going to have to lose that much from H2O and CO from the reactant. So we put a minus X for the reactant. So we're going to lose reactant, so that's a minus X, and we're going to form product, so that's a plus X. Now what we do is add these columns together to get what's good, the values are going to be at equilibrium. So for H2O, we're going to have 0.1 minus X, and for CO, 0.1 minus X. For CO2, we're just going to have X, and for H2, we're just going to have X. So this is what our ice table looks like. Now we've got to plug it into our equilibrium constant expression. So we're going to write our equilibrium constant expression. And K is 23.2, so we've got that. So this is what it looks like. So we're going to plug these values down in this last row where equilibrium is. So let me circle that. These are the ones we're going to be using right here in our equilibrium expression. Okay. So we're going to plug those in. So that's what it's going to look like. Now in this case, we have x times x over 0.1 minus x times 0.1 minus x. Well, since this is a squared value and this is a squared value, we can take the square root. That's kind of a nice simplification that we can do. We take the square root of both sides. And when we do that, we end up with this, x divided by 0.1 minus x equals plus or minus 0.84. Let me go back. So when you take the square root of 23.2, you're going to get plus or minus 4.84. So don't forget to put the plus or minus in front of that when you do the square root. That's important. So if we solve for x, we get x equals 0.0828 or 0.1262. Let's look what we started with. So we started with 0.100 molar. Well, we can eliminate one of these now. I think we can eliminate 0.1262 because that's greater than what we started with. So we can't lose more than what we started with. So we can delete that. And so what we're left with is 0.828 molar. So that's what our x value is. So that's not what the equilibrium concentrations are. Well, I guess that is what the equilibrium concentrations are for CO2 and H2, because we just plug in X, plug in our 0.828 for X in our ice table at equilibrium. But we have to take 0.1 minus 0.828 to get our concentrations for CO and H2O. So if we do that, that's what we end up with. There are equilibrium concentrations now in the ice table. And does that make sense? Let's see. We said K is 23. It means this reaction favors product. And so if we look at the concentrations of the products compared to the reactants, indeed, there is more product than reactant. So that looks good. So just qualitatively, a quick glance at our final numbers, they look okay according to what the equilibrium constant is. But we can check that, can't we? We can plug those values actually into our equilibrium expression down here, CO2 times H2O divided by H2O times CO, and see if we get 23.2. So let's do that. So here's our check. We're going to plug our values into our equilibrium constant, multiply it. Does that equal 23.2? And it does. So lo and behold, they match. So that's perfect. That confirms our that our calculation is done correctly. So we did a trick where we just did the square root of this value. We took the square root of this because that came out really nice. But that's another way, a more generic way you can solve these problems that always works, and that's using a quadratic equation. So if we multiply this out and solve, if we multiply all these squares and try to solve for x, what we're going to end up with is a parabolic equation where we end up with x squared x and a non-x value. And if we set all this equal to 0, we have an equation that we can solve using the quadratic formula. And in the quadratic formula, showing down here in the lower corner, we have A, B, and C, and A is the coefficient, I guess you could call it, for the x squared, and B is a coefficient for x, and C is a standalone value. And so in a quadratic, what we'll do is just plug in those values. So x is going to equal minus b. So b is minus 4.64. So minus a minus is a plus. So we get 4.64 here, plus or minus the square root, minus 4.64 squared minus 4ac divided by 2a. So when you do that, you get x is equal to 0.028 and 0.1262. You always get two values when you solve a quadratic equation. So again, we use the same reasoning we did previously, that 0.1262 is too large. And our answer is 0.828. It's the same answer. The quadratic formula is a little more involved to solve. I think so anyway. But I know some of you probably have a calculator that will solve a quadratic formula where you just have to plug in the A, B, and C. If you have a calculator that solves a quadratic formula for you, that might be the way to go to solve all these problems. So this, this solution using quadratic formula always works. All right, so I think that's the end of the slides. So let's go to our worksheet here. So this is worksheet 13, and the top of this worksheet, I won't go into it, it's what we just covered. It goes into solving or using an ICE table to solve an equilibrium problem. So in this first problem here, let's see where it says, what is the equilibrium concentration? So let's zoom in on the question. The question is right there, right in the middle. What is the equilibrium concentration of all species if initial concentration is H2 equals I2 equals 0.240 molar? So this is similar to the problem on the PowerPoint, but the equation is a little different. So we have H2 plus I2 is in equilibrium with 2HI. The equilibrium constant is 54, so that's another equilibrium constant that favors products. So there's our ICE table. We have 0.240 for H2, 0.240 for I2, and 2HI0. The change is going to be minus X. We're going to lose reactant. We're going to form product. This is an important point. We're going to form 2X. So this is because of the stoichiometry. If we look back at the top, we form 2HI. So when you make your ICE table, we're going to lose X number of moles from H2 and I2, but we're going to produce 2X moles of HI. So that's really an important point. So when you have a coefficient in the balanced equation, that appears both in the equilibrium expression, but also appears in your ICE table. So you can't forget that. So we have 0.240 minus X, 0.240 minus X, and 2X for HI at the equilibrium. So we're going to plug this into our equilibrium expression, and this is what we get. Over here we get 2X squared over 0.240 minus X times 0.240 minus X. Well, this again is a perfect square, so we can take the square root of that on both sides like we did in the example, If we do that, we get 2x over 0.240 minus x. That's going to equal plus or minus 7.369. So if we solve for x, here's the step-by-step way. We solve for x here. So if we multiply both sides by 0.240 minus x, we get 2x equals 7.369 times 0.240 minus x. That's going to equal 1.7685 minus 7.369x. Now this, remember, when we took the square root of 54.3, we got plus or minus 7.369. The solution down here is for the plus 7.369. If we solve it for minus 7.369, if we put a minus here, then the signs here will change. This will be minus 1.7685, and this will be plus 7.369. Anyway, we're working with a plus 7.369 as the square root of 54.3 right now. So if we continue to solve for x, we end up with, we're going to add 7.369 to both sides. So we get 9.369x equals 1.7685. We're going to solve for x, we get 0.189. Now, if we did the other one, if we started with a minus 7.369 and multiplied this out, what we would end up with is an x of 0.3294. Oh, can't see that. We'd end up with an x of 0.093. So that would come from this. Would come from the minus 7.369. Okay. Now let's inspect these two answers. We have 0.189. Okay, that looks okay. That looks reasonable. That could work. We also have x equals 0.3294. Well, 0.3294 is greater than what we started with, so that clearly is not possible. So we can cross that out. Then our check. Remember we said we can check this if we plug in these values. So we have 0.240 minus 0.189. So let's go back up to our ICE table and plug in the actual values. If we do that, we're going to get 0.24 minus 0.189, we get 0.051. Okay, we're right here now. 0.051 for both of those. And then we go 2 times 0.189. We get 0.378. So if we wonder to write down what our equilibrium concentrations are, that's what they are right there. But let's check now. Let's check to see if this works out. So if we put our 2 times 0.189 for the HI, because it's 2x, divided by 0.240 minus x squared, because there's 2 of them. Again, it's this times that. We get 0.1429 divided by 2.601 times 10 to the negative 3. We divide those, we get 54.9. 54.9 isn't exactly 54.3 if we go back up to the top of this. You can see our equilibrium constant was 54.3, but that's because of rounding. Now I checked this without rounding and put a few more sig figs in there, and it did come out 50, I think it came out 54.2 instead of 54.3. The 54.9 is close enough. That means you probably did it correctly. Now you can solve this one using a quadratic equation also, but I think for me, taking those squares is the easiest way to do that. Now in the next problem, let me see, let me just go like this. In the next problem, it's the same reaction, H2 plus I2 is in equilibrium, and I should have two arrows here. Should have an arrow going back and forth. Since it's an equilibrium reaction, the 2HI, K is 54.3. In this case, we're starting with a mixture of reactants and products. So we have H2 is 00623 and I2 is 00414. These are all molarities. And HI is 0424. So which way must the reaction go, forward or reverse as written to achieve equilibrium? Well, this question is a leading question. It gives you a hint of what you need to do. So we need to calculate Q. Remember, Q will tell us whether the reactions are going to go forward or backwards. And so Q has the same expression as, same form, I should say, as K. And remember, Q is equal to K only at equilibrium. So let's focus in on Q. So we're going to solve for Q. We're going to plug in the values that are given for HI, H2, and I2. And in this case, you just plug in the values that are given for HI. You don't multiply times 2x or anything like that. You do have to square it because of the coefficient in the equation. So when we plug that in, what we end up with, plug in those values and multiply and divide, we end up with 69.7. For Q, well, that's greater than KC, which is up there at the top. It's greater than 54.3. So that means the denominator is too high. It means we have too much product. So that means this reaction is going to have to shift left. It's going to have to go in the reverse reaction to reduce product and increase reactant. So that tells us how to set up our ICE table. It means we're going to have to subtract some chemical, subtract a few moles per liter from the product and add it to the reactants in our ICE table. So when you have a problem where you're given the concentrations of all the components in the equilibrium, you have to calculate a Q first to figure out how to set up your ICE table. That's an important step. They don't always tell you to do that. In this problem they did, but sometimes they don't. So that's what I said. The product is too high, so equilibrium shifts left. We have to decrease the product and increase reactant. So we're going to set up our ICE table. So I've already set up the ICE table. Here's what it's going to look like. So H2, I2, HI initially, I go back and look, looks like I wrote in the correct values. That looks okay. So what changed? We're going to minus X. I should say we're going to add X to H2 and I2 because we need to form reactant. We have to subtract 2X from HI. Now if I said, now we could set this up differently. We could say minus X for HI, but then it would be plus 1/2 X for I2 and 1/2 X for H2. I'd rather not deal with the fractions, so I'm going to say we're going to add X to H2 and I2, and we're going to subtract 2X from HI. So our equilibrium concentrations are shown at the bottom. Those are what we're going to plug into our equilibrium expression. That equals 54.3. and then solve for x. So substitute the e values into K1 and solve for x. So here's what it will look like. We have 0.0424 minus 2x squared divided by 0.00623 plus x divided by 0.00414 plus x. And that all equals 54.3. Now, unlike our previous example, we can't simply take the square root of this and get the solution, because the square root of if you take the square root of this part, it doesn't come out nicely. So just can't take the square root this time. So we're going to have to multiply everything out and expand it. If we do that, we end up with 1.798 times 10 to the minus 3 minus 0.1696 x plus 4x squared. And on the bottom, we have 2.579 times 10 to the minus 5 plus 0.0137x plus x squared. Again, we have to try to get this into a polynomial that we can solve using the quadratic equation. So we have to get all the x variables with x on the one side and get it all equal to 0. So we'll multiply that out. We end up with something like this. A couple of steps here. I'm not going to go through them. But we'll finally end up with 0 equals minus 4.02 times 10 to the minus 4 plus 0.7327x plus 50.3x squared. Okay, let me zoom out. So if you want to take a shot at this, you can look at what I have here and work it through, or work it yourself to see if you can get it. So this takes a little bit of time. Just to write it down takes time. There's a lot of numbers there. Anyway, when we finally get it into our form to solve a quadratic, we have our A, our B, and our C. So we're going to solve our quadratic equation, plugging in the A, B's, and C's. And when we do that, we end up with x is equal to minus 0.7327 plus or minus 0.7860 divided by 100.6. Well, since this is a negative, see our B is a positive value, so when you plug in the quadratic, it becomes negative. Well, a negative, when we take our square root, we get a plus or minus. Well, a negative value just doesn't make sense, so I didn't even write that down. So the only value I wrote down was our positive value, which turned out to be 5.30 times 10 to the minus 4. So that's the x. It's 5.30 times 10 to the minus 4. So the next step would be to write down what our equilibrium concentrations are, which if we go back up to our ICE table, it's 0.00623 minus 5.3 times 10 to the minus 4. Oh, excuse me, plus. Sorry, we're adding reactant. Plus 5.30 times 10 to the minus 4. 00414 plus 5.3 times 10 to the minus 4. And over here we got point for HI, which is the product, 0.0424 minus 2 times 5.3 times 10 to the minus 4. So lastly, we do the check. And when I say do the check, remember subtract 2x from HI. Well, I did the check. I want you to do the check and see if it turns out okay. I did the check, and I believe it did come out to be 54.3. So that's another thing is that we formed a little more reactant. We decreased the product. but we didn't decrease it very much. So if you remember, if we go back and look at our Q, the Q was above, was greater than K, but not largely greater than K. So we would think, well, we don't have to change it very much. We don't have to change these concentrations very much to get down to K. And indeed, we didn't. So just kind of doing a rough estimate, we didn't change it. We lost a little bit of product and we formed a little bit of reactant. And that turns out to be just enough to reach equilibrium. So you can do the check on your own. That's the easy part. And that's really the end of the presentation and the end of chapter 13. There are some of these problems to do in the Newton. They take a little longer than the problems we've worked on previously because you just have to crunch through those quadratic equations sometimes. So that's all for now. And that finishes up chapter 13. So take care.